So welcome to the XSEDE MPI workshop. I'm John Urbanek, coming to you from Pittsburgh Supercomputing Center. This is the workshop that most excites me as a parallel programmer, because this is the most powerful of all the parallel programming techniques. Now, our Laplace exercise is awesome in a couple of ways. One of which is that it's just a great example of the kind of power that MPI can bring to solving problems scalably. It's a good example of an algorithm that will scale well up to hundreds of thousands of processors, and this is the same algorithm we're going to use here. Applies to many scientific problems. In particular, this halo or ghost exchange technique we're going to use is perhaps the most common way to break up MPI problems into pieces. So those are all very good, but more importantly, if you complete this exercise, you are for real an MPI programmer. You are not going to complete this exercise accidentally by cutting and pasting code and hoping things work. It's a legit serious problem. And so if you get this working, if you complete this problem on your own, you really do know MPI. Now, you're not a master of it. You're not super experienced. There's still plenty more to learn, to become more efficient at it. But you can call yourself an MPI programmer when you complete this exercise. So please do give this your best effort. So let's jump into it and see what the exercise is about. It's a simple physical problem. I like it because it's intuitively obvious what we're trying to do here. We're trying to model a metal plate that's initially at 0 degrees, and we're going to heat it along its edges in an interesting fashion so that it should acquire some kind of temperature gradient. Long term, it should eventually settle into a steady state. And if we heat the plate up like this, where we have a very hot corner down here, we have a heating element that's 100 degrees, and the temperature tapers off to 0 degrees in both corners and 0 degrees on these two edges. We might expect that our final configuration might be a gradient, something like this. We have the metal plate ends up being very hot in this corner and cooler as we go across the plate. And so this is how we should expect the result to look. The way we solve a temperature problem like this is to solve the Laplace equation. The Laplace equation here models a lot of physical problems. It models temperature without any sources in the middle of our field right here. It also is very applicable to electrostatics and fluid flow problems. So it's a very generally useful mathematical physics equation. However, I'm assuming that most of you are not comfortable with this particular equation. Maybe your mathematical physics is rusty or non-existent, and that's fine. You're going to be fine, because the intuitive physical nature of this problem is going to be all we need to understand, because the actual solver to solve this mathematical equation is very simple. Using Jacobi iteration, all we need to do is keep going over this metal plate, the grid points that make up this metal plate, until all of the points look like the average of their neighbors. That actually is what Laplace's equation really implies. Laplace's equation mathematically says that every point is the average of the points around it. And the reason this is such a physically useful equation is this reflects an awful lot of physical situations. In the case of temperature, you might expect that if you have a very hot rock and a very cold rock, and we sandwich some rock in between the two, that middle rock would become lukewarm, essentially, an intermediate temperature. That's Laplace's equation at work. It says every point's kind of the average of its neighbors. And so the mathematical method we'll use to solve Laplace's equation here is Jacobi iteration. And it is simply saying we're going to take every point and set it equal to the average of its 4 neighbors. We're going to take the neighbors to the north, south, east, and west, add them together, divide by 4. That's the average of the neighbors, and that's what we're going to do. We're going to keep sweeping over this grid, and we hope that eventually the solution will converge upon the correct answer. And indeed it will. This is a reasonable assumption. And so this I hope makes sense to everybody. I hope it's a nice, simple, physically intuitive numerical method. And it looks just this simple when we turn it into code. Here's the C code right here with a couple of nested for loops going over the I and J indices. Here's the Fortran code, and all we're doing, again, adding our 4 neighbors together and setting it equal to the 1/4 of that, get the average. Now you will notice here we actually have 2 arrays here. We have temperature and temperature last. And this is kind of necessary because as we scan over the grid, we don't want to worry about whether our neighbors, some of our neighbors have been updated already to our current iteration, and some of them haven't. You can imagine if you're iterating over this grid, like so, that we're going over the grid in this raster pattern, that maybe this point we've updated, and then we come down here and we've updated this point, and we get to this point, then to use our 4 neighbors, 2 of them are updated points and 2 of them are not updated points. And that's not quite as obvious what's going on there, whether that's acceptable or not. Actually, in reality, it might even be a little bit preferable, but at any rate, we want to keep things nice and simple. And so we want to make sure that when we're updating this point, we're using all points from the last time step. So that is what this temperature last is for. This is the last time step. This is our current time step that we're figuring out. And when we're done with our new time step, we'll just copy the temperature last. As a matter of fact, this is what the code looks like. So here's the C code, the kernel, as we call it, or kind of the scientific guts of the code. We're going to have a while loop. It keeps going until we come up with our answer. How do we know when we come up with our answer? Well, when our worst case temperature change from one iteration to the next is very small, when it's quit changing from one iteration to the next, we can call that done. And we'll do is we'll find the worst of all the grid points that we're changing. We're going to find the worst case temperature change, the maximum temperature error. And when that is less than some number, and then we're going to pick 1/100th of a degree, when that change is less than 1/100th of a degree, we're going to call it a day. We're going to say we're done. So when we quit changing more than 1/100th of a degree from one iteration to the next, we're done. We're also going to give ourselves one more other out. So when we're developing the code, somebody might have a kind of a threshold of patience. The user might say, I don't want to run more than 100 time steps or 1,000 time steps. And so they can set, the user will also have the opportunity when they run their code to enter in a limit. So the user can set a limitation for how many iterations to run. Otherwise, if they set this to a very large number, and not to be a spoiler, but this thing will solve itself in about 3,300 time steps. So if I set this equal to 4,000, then the problem will solve itself. If I set it equal to 100, it'll stop after 100 iterations. So that's how long our loop's going to run. Inside the loop, we do exactly what I just said. We find our new temperature based on our 4 neighbors from our last time step. We're going to then copy our new temperature to our last temperature time step before we go around the loop again. So while we're doing that, that's also a convenient and efficient time to look for our worst case temperature change. So we're going to check every DT. We're going to find the worst DT between this temperature and temperature last as we copy these points over. We're going to copy them over. And every once in a while, every 100 time steps, we're going to print out some partial results to see what's going on. We're not going to dump the whole array because that's 1,000,000 points, but we'll dump some small corner of the array and make sure that something good is happening. That's the whole code. That's the whole loop right there. So I hope everybody's kind of following along with what's going on. There are a couple of helper subroutines here in the code that are useful to us. The initialize routine is where we set things up. We set the plate equal to 0, and then we set the boundary conditions on 2 of the edges equal to 0, and on the other 2 edges to that kind of linearly increasing temperature along the element. And once in a while, we'll print out, as I said, some results. We'll print out the bottom little corner diagonal of the grid and make sure something's happening. It's kind of a hot corner down with the temperature set to its highest value, and we'll make sure that things are changing. So it gives a little check. Here's the entire C code, and you don't have to squint at this. This is here just so you can see. It's not a lot of code. So there's not a whole lot for you to understand. This yellow part's the kernel we just talked about. These are the subroutines we just talked about. So there's not a whole lot to this code. You should be able to kind of go through it and understand it completely before you start working on the problem. It shouldn't be too much to worry about. Here's the Fortran version of it. It's exactly the same logic line for line. So once again, we have a while loop, and we're going to keep going until either our temperature really quits changing less than 100th of a degree, or until we run out of allowed iterations. Here's the loop that does calculates a new temperature. Here's the loop that copies the temperature for temperature last and also checks the worst case temperature change while it does that. And here's where we print out the results every 100 iterations. Here are our helper subroutines once again. Here's where we initialize the plate, and here's where we track our progress. Here's what the entire code looks like all together. Again, not a lot of code, so take a chance, take a second to review all the code before you dive into it and start trying to parallelize it, because your goal here is going to be to parallelize this. Is this code outside of the PDF, somebody asked? Yes, indeed. It is sitting in your exercises directory. I'll point you at exactly where it is. So we'll get to that in a moment, but it is sitting there in your exercise directory. Do not try to cut and paste this from the lecture slides, or God knows what little character transpositions will take place. Okay, so we need to take and break this problem up into pieces so that it runs faster. That step is called domain decomposition, and it's the first thing you do pretty much when you're parallelizing an MPI code. It's the most important thing you're going to do. If you do this right, things are going to sometimes almost write themselves. If you do this wrong, it can be very bad news. You can struggle for a long time to ultimately end up with a code that doesn't perform well, doesn't scale well, and most of your effort might be wasted. So doing this step right is very important. Fortunately for you, most problems these days, classes of problems, there's a lot of good guidance and precedent as to how you should do this domain decomposition. There certainly is for something like a square metal plate. One of the things that you don't want to do, an amazing number of people will do, is you don't want to take and right away copy the whole metal plate around everywhere. So all 1,000 by, our plate's 1,000 by 1,000 in this case, by the way. So you don't want to take our 1,000 by 1,000 metal plate and say we're running this on 4 PEs, because that's what we're going to do. Our problem will be stuck on, we'll stick ourselves to 4 PEs. We don't want to take and just copy the plate onto 4 PEs, and then each PE works on a small part of the plate, and then we combine the results together somehow or other. People have this tendency to do that, and that's a terrible thing to do for a lot of reasons. One of which is that this code will never scale. One of the great things about writing an MPI code is not only that it runs faster, but that you can run larger or more refined problems with higher definition. In other words, we could take our metal plate here, and let's say, for the sake of argument, that our metal plate takes up most of our memory. So we're running this on 100 gigabyte nodes, and our 1,000 by 1,000 metal plate takes up most of our memory, which, excuse me, isn't even close to reality, but let's pretend it is. So now, one of the benefits of doing this with MPI is that if we parallelize this, now when we run on 4 nodes, we can run a 4 times bigger problem, 4 times bigger grid. Or when we run on 1,000 nodes, we can run 1,000 times bigger problem. So if you take, for example, our weather problem we've been talking about, one of the reasons that the weather service runs on a supercomputer with MPI isn't just so that they can run faster, it's so that they can run a much bigger grid than would ever fit in memory on a single PE. And that's exactly what you accomplish when you do a good domain decomposition, as opposed to this, where we're copying the whole metal plate around. If we're copying the whole plate around, things can never scale up. We were still at the memory limit of all 4 PEs. So that's one reason it's bad. Another reason it's bad is we start sending very large messages around to keep these things synchronized at the end of every time step. So there are a variety of reasons that this is just a terrible idea. But at any rate, what you don't want to find yourself doing is ever copying some large data structures around so that they're synchronized on all the PEs. If you ever find yourself taking the large data structures in your code, and most codes have some very clearly large data structures. Our weather code, it's going to be the weather map itself. So I'm not talking about some little individual variables here and there, like the date or the time, or how bright the sun is, or whatever. The big arrays that you've got in your code, you should never find yourself reproducing and copying them around your code. Instead, you should find yourself breaking them up into smaller pieces. When you're done parallelizing your code, you should have smaller pieces, smaller data structures, not bigger ones. And so that's what we're going to do here. And that's what we might do with a much smarter decomposition, where we take our metal plate and break it up into a bunch of 500 by 500 pieces. 4 or 500 by 500 pieces would be a fine domain decomposition. And now this 1,000 by 1,000 array, it no longer actually exists anywhere except in your head. So when you're working on this Laplace code and we break things up, we're still going to have somewhere 1,000 by 1,000 array. So it's in an abstract world, because that's our problem size that we're handed. But nowhere as a variable is there ever going to be an array anymore that's 1,000 by 1,000. If we tried this decomposition right here, you'd have a 500 by 500 array on each one of our 4 PEs. 1,000 by 1,000 array no longer exists. This is nice now, because first of all, we could scale the problem up if we chose to, but now we're sending small messages around. There's these little strips along the edges. This is a fine domain decomposition. And if you propose this to me, I would say, fine, go for it. However, I'm going to propose one that's even a little bit simpler for you, since you're just beginners. And that's to break things up into strips like this. We're going to have 4,000 by 250 strips. And this is nice because that means we're only sending messages in one direction. Not that it's that hard to send messages left, right, and up and down. And we'll cover that tomorrow. We'll look at some alternatives, and we'll see how easy it is to do. It's not hard to do. But to make life simplest for you right now, we're just going to send messages up and down. And so that means we're going to break our metal plate up into these 4 strips like this. And this is also a fine decomposition. As a matter of fact, it's really nice in that we can now take and decompose our strip. What if I said I wanted 5 strips instead of 4? No problem. We could do it like this. But if we wanted to run this on 5 PEs, it's a little bit trickier. So nothing wrong with this decomposition, and it's the one we're going to go with. So in our C code, we're going to find out that what we do is we take that original 1,000 by 1,000 array, and it now is no longer going to exist. It's now only going to be these 250 by 1,000 arrays. And actually, after we get done adding on our boundary conditions here to our metal plate, it's going to be actually 1,002 by 1,002, but we'll look at the details a little bit more after we look at the trickiest detail of breaking this metal plate up, which is that we still need to communicate between these regions. We haven't just made 4 isolated metal plates. This isn't now 4 independent problems. This is one still metal plate. So along these edges where the temperature is affected by our neighbors, we need to communicate data. We need to make sure that each one of the metal strips knows what's going on in its neighbor. And we're going to do that with a technique that's very, very common, again, and universally useful across many different types of applications, which is usually called halo decomposition, or halo cells, or halo zones, or ghost cells. And so I'll call them ghost cells here. You'll hear halo used quite commonly. And the reason for halo or ghost cells, the reason for the terminology, is that between the regions where they have to communicate, we're going to put an extra fake row of data that really represents the data from our neighbor up here. So that when PE0, for example, PE0 on its southern border, PE0 has row 250. That's its bottom of its metal plate that it's really responsible for. When PE1 is trying to calculate row 1 right here, it needs to know what the temperature is up here in row 250 of PE0. So it needs to know this information. So what we do at the end of the time step is we take row 250 here, and we'll make a copy of it into row 0 of PE1. And so PE1 isn't going to worry about calculating row 0, but it's going to use row 0 in calculating row 1. So that's its neighbors to the north. Meanwhile, PE0 for row 250, its bottom real row needs to know what's going on in the topmost row of PE1. So it needs to get a copy of row 1 from PE1 up here into PE0. And so we need to copy these buffers around. So these are kind of overlapping rows right here. So these are our real original coordinates, go from 1 to 250 here, 251 to 500. But in reality, our coordinates go from 0 here, which is a boundary condition up here, to 251 here, which is this ghost row. And then row 0 here corresponds to row 250 up here, and it's the ghost row copy of it. And then PE1 starts with its real row 1 here. It's really calculating out of our original coordinate system, row 251. So that's an incredibly complicated verbal statement, but I hope that staring at this diagram, this all makes sense how this works. And it's necessary. You're going to have to understand this in order to make this, this code work. And it's good to master this technique because it's, again, going to be so applicable to many, many domain decompositions that you come across in MPI, where you break a problem into pieces, but you still need to know some nearest neighbor communication. And so this is the general technique. So I hope this makes sense to everybody. Now the question might arise of, well, okay, how do we send now instead of one, so far we've been sending one number, one floating point number or one integer, how do we send a whole strip of data? Well, the nice thing about this decomposition is it's very easy in MPI. All we need to do is point it to the beginning of the row and then use our count argument to tell it how many to send. And so that's exactly what's going to happen. We're going to just point it at the beginning here of this grid point and say send 1,000 of these, and it's going to send the whole row. However, this does demand kind of that all the elements have to be contiguous in memory. When you tell MPI to send a bunch of something, a strip, it's going to send a bunch of elements next to each other in memory. And that's going to work out okay here because in C, these arrays are laid out like this. This is the first row, and then in memory, the next row comes down, and then in memory, the next row. So we're lucky, if you want to call it that, it's the way we broke the problem up, in that we get to send this entire row here by just pointing it at the first element and send the next 1,000 in memory, and it's going to work just fine. So that's what we're doing. Now in Fortran, we're going to find out that it's actually the opposite. Fortran lays things out in memory, the exact opposite, lays things out so that they go down the columns in memory. This is an unfortunate difference in convention between Fortran and C. Caused many a bit of confusion over the years, although those of us that work with math libraries and science libraries have long since gotten used to the fact that, yes, you've got to transpose arrays when you copy them between Fortran and C. And since much of the world's mathematical libraries are written in Fortran or C, you have to kind of worry about this a little bit. However, like I said, I've defined the problem so you don't have to worry about it so much. So in other words here, what's going on is that in C, when we send it, we point an MPI send to an element in an array. So in this case, we send it to 3, 1. And in C, 3, 1 means it's going to count down here, starting with 0, 1, 2, 3. And 1 is going to be counting with 0 to 1. It's going to start here. And then we're going to send 4 elements. It's going to send this strip of this array. In Fortran, if you do 3, 1, because Fortran works with a different orientation of this array, Fortran is going to start counting out from 3 here, 1, 2, 3, and then 1, and it's going to go this way contiguously in memory. So Fortran and C are exactly opposite in the way they work through arrays. Again, for many of you, it will never be an issue, but it does just mean in our case here, the Fortran problem, we're going to break this thing into strips going the other direction. But I do want to, the reason I bring this whole thing up here is because I hope you all are aware of the fact that arrays are laid out in memory like this. They have strides in memory, and you always want to make sure that the innermost loop of your codes, whether it's parallel or not, whether it's Fortran, C, Python, whatever you're using, you always want to make sure the innermost loops of your code work over the contiguous memory and they're not skipping all over the place in memory. In other words, in our code, if you look carefully, you'll notice that our innermost loop of our temperature code here for C is this J index here is the last index, because in C, you want to make sure you're iterating over J, and then your next loop out will be I, and if it was three-dimensional, and we had another loop out here, it would go in this order. If you look in Fortran, our innermost loop is actually I, the first index. So we work from the leftmost index in Fortran, you work from the rightmost index in C, and it's very important you do that in just regular serial code. Otherwise, you get terrible performance because things are skipping all over memory. So, like I said, I don't feel bad about having to introduce this notion of paying attention to what's contiguous in memory. Very important just to get good performance out of any code in any language you're working in. Okay, so in our case here, we know that we want to send a strip of data up in our C code right here. So we can write some code. There's different ways you can write this. There's not one single way it's going to work out. So I could write some code that says something like this. If I'm not PE0, then the up, my destination up is my PE -1. So I do a send and they'll all go up, and that takes care of sending messages down. But if you play around with MPI, you'll notice there are different convenient ways of doing this. We'll look at some more ones tomorrow. So there are things like, for example, MPI has something called MPI proc null, and it's basically a black hole. You can send messages to it. It will just, there won't be errors. It actually will save its time. It won't even waste time sending a message there. It knows that just disregard that. So I could write code that looks like this. Up equals my PE -1, my PE equals 0, up equals proc null, and I could send messages up. Lots of different ways. I just want to point out there's not one single way you have to find yourself doing this. But what you do want to do at the end of the day is make sure you send messages up to, for one phase of your communication, to send that strip up. You've also got strips that you want to send down as well, and you've got to receive those messages. Now in Fortran, as we just said, the orientation is exactly the opposite. So our strips are going to run vertically like this, but it's the exact same notion with ghost cells right here. So we have ghost cells and ghost zones that we want to send. So we want to make sure that this row 1 here gets copied into this ghost cell. And meanwhile, this row 250 here, or column, I should now call them columns, this column 250 gets copied into column 1 over here. So it's the exact same thing, same kind of message passing, except we're passing to the left and the right this time. And so you're going to find yourself starting out with a serial code here. You're going to find that the compute phase of the serial code, which is where all our number crunching is done, is largely going to remain unchanged. You're not going to have to change a whole lot there. And this is, again, typical of most MPI codes. You're not going to have to mess with the structure so much. On the other hand, the communicate phase is where most of your work is going to get done. You're going to have to spend some effort getting the message passing so that the messages go left, right, or up and down properly. And that's where most of the thinking has to be done. You're going to have to make sure you get all the indices just right. I'm sorry you're going to have to think so much about indices, but hey, welcome to programming, right? You're going to have to get the indices right, and you're going to get that done. And you're going to find out that you're going to end up with a code that has a compute phase and a communicate phase, and that's very typical of MPI codes as well. The boundary conditions are also going to take a little bit of thought. You're going to have to go outside of just that main while loop there and fix things that involve the temperature array and the temperature last array everywhere. This is where MPI requires a lot more effort than other parallel programming techniques like OpenMP that only work on a node. With MPI, everywhere you do a decomposition of a big data structure, you have to go throughout the entire code and make sure you tweak things so that it works right with that new decomposition. This is not always good. This is particularly bad news if somebody hands you an 80,000 line code that you've inherited and you look through it and find the main data structures and do a decomposition. You are going to have to dig through the entire code, all 80,000 lines. And sometimes you get lucky. It's just, you know, a lot of the code doesn't involve the main data structures or whatever, but you have to check. That's a lot of potential. It's a lot of commitment. And that's why MPI ports can take a lot of time and a lot of effort. If you're writing a code from scratch or it's your own code, you're lucky it could be a lot less. But the point is, you don't get the luxury of just going in and tagging a subroutine or a loop here and there, like you might with some other more limited parallel programming approaches. With OpenMP or GPU programming, we might hope that we can just go and fix a loop, and that loop will run well on a GPU. With MPI, you've got to go through your code and find all of your global, find all the big data structures and find all their occurrences. In this case, that means temperature and temperature last are also floating around our boundary conditions. So you're going to have to go into the boundary conditions, and where they used to be pretty simple like this, you're going to have to make sure the logic is correct. So that's going to take a little bit of effort. Now, there are two ways to approach this exercise. You can either just start with the serial code that you have sitting there in your exercises MPI directory called Laplace serial C or Laplace serial F90. You can start with that code and just start plugging in MPI routines, or you can take a template version I've got sitting there that has some hints. And a template version looks kind of like this. Here's the C version of the template code where I've got these hints, and there are these greater than signs here, where I have some comments saying where you might want to consider putting in some MPI code. And they're not really big spoilers. Matter of fact, the hardest part of your code, the communication phase, I mean, this is what it says right here. So you've got a lot of thinking, a lot of work to do, but at least gives you some hints. And the Fortran one looks very much the same. So you can use the template codes if you'd like. And there are lots of places here to, to mess up and stub your toe as you go along here, and you've got to figure them all out and debug this code. That's why, as I said, when you're done with this, you've got a real accomplishment. You're an MPI programmer. You're not going to get this by randomly cutting and pasting and hoping it works. You've got two main data structures here, temperature and temperature last. You've got the boundary conditions and the go zones. You've got to keep track of those. And every iteration, you've got to send some messages around from temperature to temperature last, or maybe from temperature last to temperature. You've got to think about it. So you've got to think about all these things, and they're easy and inevitable. You mix a little bit of it up. So it's going to take you some time to line it all up. You're going to do a lot of this problem basically with a piece of notebook paper, making sure you get your indices right and you send messages and receive them from the right place. There are multiple solutions, so there's different ways to deal with this, and you can, you're going to have your own personal solution. How do you know you're correct? Well, the one obvious way might be to say, okay, what if the solution converges at the same time? You run the serial code, and I said it converges in 3,372 time steps. So if you write the parallel version and it also converges in 3,372 time steps, then surely that is the correct solution, right? What are the odds that a broken code is going to converge in the same number of time steps? Well, turns out that's not quite true. And by the way, that surprised me way back when I first did this too. I ran it and I'm like, wait, this converged in 33. This converged, even though I know some things are broken here. And it surprised me until I actually looked at what's going on here. And the reason that even a broken code can converge in exactly 3,372 time steps, if we look at the actual result when we're done, the temperature output, and here's a little plot of our temperature gradient going from the hot corner to this is mostly PE3 and PE2. And if we look at the working code right here, the bottom right corner is where most of the action is going to be. And it converges down here last because it's the hottest corner. Here's a version of the code running where I actually ripped out the MPI routines. So it's very broken. It's got these weird dips in it between PEs. So I mean, here's the boundary between PE3 and PE2. It's got this weird dip in here. This is obviously a broken code. But guess what? This one still converges at 3,372 time steps because it turns out that this is the last part of the code to converge this hot corner, regardless of whether it's working right or not. And so unless you do something very, very wrong. So this is the part that determines when it finally converges. So even if it's messed up, it still converges in the same number of time steps. So if you want to be sure you've got the right code, you have a choice. You can visualize things. You can dump the whole thing out and visualize it. And that's not a bad thing to do. So I printed the whole thing out and dump it and visualize it. That's what I did. I used Excel here. Most of you will probably want to use something a little cleaner, like Matplotlib is how I actually do this in the real world. And you can visualize this. And very easy to do, and you can see that the solution looks right. Or I'll give you a little bit of a hand up here. I'll tell you that here is what I call a magic point. Here's a point right on the boundary, and this point here, which happens to have coordinates 750, 900 in C, or 900, 250 in Fortran. This point right here should be about equal to 1. And if that point is about equal to 1, you're probably doing the right thing. If it's not equal to 1, you probably still have a broken code. So you have multiple ways to verify your solution. But the seemingly obvious one that, hey, what are the odds that a messed up code happens to stop at exactly the right time step? Sadly, that doesn't work here. But here are some ways that do work.